Well, when I was abruptly cut off when I was introducing Unit 3.1, so I'm going to call this one Unit 3.1.2, and this is going to be the rest of the intro section through slide number 19. So we talked about Wegener, talked about some of the evidence that he used, evidence of the time. Again, he's in the early 1900s, so he didn't have technology like submarines and sonar. He didn't have satellite data, so his data was good for the time, but looking back, some of his ideas were crazy. If you ever saw The Land Before Time, continental drift is sort of like the dinosaur babies, Sarah and whoever the rest of them are, actually sitting on one side, and the grandparents and the parents sitting on the other side, and there's an earth shake, which tended to be an earthquake, and then the earthquake moves and the continents just move apart. No real explanation on why they do it, continental drift. So here are some objectives to Wegener's idea. Continents cannot plow through ocean rock. They're not like these ice plow ships, icebreakers that actually sit up on top of the ice and then break through. We don't see any evidence of the ocean floor actually showing us now that the continents plowed through them. So it's not like icebreakers. There is no proposed energy source to actually make this. It wasn't wind, it wasn't tides. Tectonics themselves or earthquakes themselves couldn't do this pressure because North America would be moving the other direction. And, again, it's not due to gravity, waves, or tides. Evidence for the idea that plates are tectonic, magnetic field and paleomagnetism. So we actually take a look at rock the way they are today, forming today, and notice that rock that formed in the past, paleomagnetism, is different. Minerals inside of magmas, metallic minerals, actually align themselves to the present magnetic field. When they're liquids, they can move any way they want to and point any way the magnetic field does it. But once the rock solidifies, these minerals actually are locked in rock, and if the Earth continues to move, that motion is locked in the rock. Magnetic field are cooled anytime the rock cools down before its Curie point. Curie point actually is the point where if you take a magma and you cool it, and the rock starts to form. That's right around 600 degrees Celsius. That's called the Curie point. It actually works both ways. If you take a rock and you heat it to 600 and keep heating it up, it will melt at the Curie point. Magnetic dip and inclination. So the dip actually looks like this, and if you take a look at rock, or if you take a look at the Earth's present magnetic field, you can see the dip angle. Sometimes it dips almost straight down, but most of these places are dipping in at an angle, and the southern hemisphere it's actually dipping out of the Earth, and the northern hemisphere it's dipping in. So you can actually see this dip angle does change with latitude. So if this rock was to turn solid today, the rock up here would actually be show this in this dip orientation, even if it was located over here somewhere. And polar wandering. Here's the North Magnetic Field. If you take a look, it's not directly at the North Pole. It's actually sitting off a little bit above Canada on the other side, and that's where the south end of the magnet, because the north end of magnets actually attracted to it. And again, it's coming out of the southern hemisphere and it's going into the northern hemisphere, and you can see it's got these weird bands. And if you remember back in physical science where you shook iron filings over a magnet, you could see the magnetic field around a magnet just like it is around the Earth. Polar wandering. If you take a look at the rock in North America and the rock in Asia, and you actually look at the way the rock points, the rocks over in Europe actually say that the North Pole has migrated this way and will continue to move that way, and North America says the rocks go this way, and those don't align. We do not have two North Poles. But if we actually move North America and Europe this way and put it into a Pangea type effect, you see that these wandering lines align themselves pretty well. Magnetic polarity reversals. We now know that the Earth is producing rock in the mid-ocean ridge in the middle of the ocean, and that rock is orientated toward our present magnetic field. And if we go a little bit west or a little bit east, we find rock that points the opposite way. And then we go a little bit more and we find it again pointing the right way, and a little bit more it's pointed the opposite direction, a little bit more. So it actually looks like either the rock is flipping around or the Earth's magnetic field actually becomes opposite it is the way it is today, and then just keeps switching back and forth over a normal time. So it is normal and reversed. Ages of changes are known. We can see it in ocean rock. We can also see it in continental rock, and age the rock different locations so we know when it happens. Magnetic anomalies are locked in to the ocean floor, and they're symmetric on both sides. So the reason the ocean floor looks like this, and we get this kind of alignment, which is normal, and then all of a sudden that rock splits and we get an abnormal one with another normal one, and then that rock splits and we have an abnormal one on both sides with another normal one in the middle. And as the ocean continues to grow, the rock solidifies, and it takes on record the direction of the present magnetic field. And then it has a stripe pattern north and south, and we'll see this again. Seafloor spreading. By the time World War II comes around, we've been looking for submarines. We start seeing these places, because if he doesn't see a submarine, it goes all the way down to the bottom, and we're starting to get a really good map of the ocean floor. And we're starting to see these places I talked about on the first slide, mid-ocean ridges, deep ocean trenches, volcanic islands that extend all the way down to the bottom of what's called the abyssal plain. And then Henry Hess, 1960, he's a oceanographer for the United States Navy, actually comes up with the idea of seafloor spreading. He's actually saying that bathymetric maps of the seafloor, the mid-ocean ridge, and that actually shows mid-ocean ridges and deep ocean trenches. And we're also seeing that the ocean crust was created at the mid-ocean ridge, so as the rock is being pushed apart, the seafloor is spreading. So now we actually do have a force. And ocean crust is destroyed at the ocean ridge. So the oldest rock anywhere in the ocean is located really close to these deep ocean trenches. Vines and Matthews, 1963, look at the magnetic strips again, and they represent changes in the Earth's magnetic field, and they do see polar reversals, and they see it symmetric on both sides. So we're actually seeing, in terms of millions of years, we actually know when it's normal, we know when it was reversed, when it was normal, when it was reversed, and we know these ages based on land rock, and we can actually see the same thing in terms of ocean rock. Age of the ocean floor by magnetic strips. If you take a look at this reddish color, it's easier to see in the Pacific Ocean because it spreads a lot faster than it does here in the Atlantic. But the same color, if you can look at that really dark reds in the middle, and it gets less and less red towards the yellows and then towards the brown. And if you take a look at it, these are actually the magnetic rocks. They also show us in terms of age. And the rock gets older as we move towards the coast of the continents, and they get younger as we move towards the Rift Valley or the Central Ridge and the mid-ocean ridges. Other evidence for plate tectonics, radiometric dating, where we actually take a look at radioactive materials, and we know that radioactive materials change from their radioactive, which basically means unhappy aspect, to more stable parents. With a very ordered time. We call it a half-life. So after one whole half-life, which they're saying is a unit of time, we have half of it left. Half of the remaining parent and half of the accumulating stable daughter cell. After another half-life, we have half of that left, so half of a half is a quarter. And then after another half-life, an eighth. And if we can take a look at the actual radioactive material, the black dots versus the red dots, the stable daughters. And after a certain period of time, we have 50% left. If this was 1,000,000 years, 1,000,000,000 years, 1,000 years, 4 seconds, it doesn't matter. It changes. And we'll do a lab about this at some point. Maybe we should do it now. Heat flows higher at the mid-ocean ridge, so if you actually look at the heat coming up through the ocean floor, it actually tends to happen at the mid-ocean ridges more so than the continents, which tend to be cooler, showing us thicknesses as well as the fact there's molten rock right under the surface. And again, this western part of western part of South America and North America, the eastern part of the Pacific Ocean actually has higher heat flow than just about any place else. Here's the mid-Atlantic ridge. You can see it actually has some yellow, so it's not a whole lot, and these are actually milliwatts per meter squared. So we're talking about a whole lot of production at some areas and very little production at other areas. And most earthquakes occur at the boundaries of plates, which I've seen you in a couple of slides. Different types of earthquakes and different types of plate margins. If you take a look at these dots, the color, the yellow, is actually intermediate. Intermediate are any earthquake between 70 and 300 kilometers in depth. The blues are actually shallow earthquakes, which are at 0 to 70. I've got those lines sort of drawn on this map, although when you try to put these lines at certain places, the pixels don't allow you to put it exactly. It should be a little closer to this 75 line, and this one should be down here at this 300, but it's not. So basically these are shallow, these are intermediate, and these are deep earthquakes. If you took a look at divergent areas, because the plates tend to be relatively thin, you get more shallow and very shallow intermediate earthquakes. If you take a look at the convergent boundaries, where this plate is being pushed up underneath South America, sort of like this one except in reverse, we tend to find even the deep earthquakes, but they're offset. So it actually shows you that this plate, this Nazca plate, is actually being pushed down underneath South America. And same thing for all these islands out here, for Japan, the Philippines. You can actually see them for the Marianas. You can also see it up here for the Aleutian Islands. The Pacific plate's being pushed up underneath toward the deep, and then this plate's being pushed towards the deep, and then toward the deep, and then toward the deep, and then toward the deep, and toward the deep. And you can see that there are some plates, especially like the Pacific plate, it's being pushed under, pushed under, pushed under. This one's being pushed under, and being pushed under, it's being pushed under. You can see the Pacific Ocean is a dying ocean. And the last slide, distribution of earthquakes. If you, again, don't pay attention to the depth, just notice there are a lot of earthquakes in some areas and not so many in others. But if you actually look at them, they don't tend to be as haphazard as somebody may expect. There are earthquakes in other areas, but most of them happen at the boundary of plates. And that is the end of this presentation of 031.2. Thank you much.